Do her here. Okay, so here we are. This is section 14.3 of our textbook, which deals with acid chlorides and acid anhydrides. So a couple new functional groups, right? Brand new functional groups. Again, the topic of the entire chapter is carboxylic acid derivatives. So far we've looked at carboxylic acids. We've looked at esters, right? And if we replace the hydroxyl of a carboxylic acid with a chlorine like this, then we have an acid chloride. So an acid chloride. It says here acid chlorides, derivatives of carboxylic acids. Again, we just swap out the hydroxyl for a chlorine. And how do you name them? Well, if you can name a carboxylic acid, which I'm pretty sure most of you are able to do by now, you can name an acid chloride. You change oic acid to oil chloride, and if it ends in simply ic acid, you change it to ill chloride. All right, so if we look at some examples here, we have ethanoyl chloride, right? Why is it ethanoyl? Because there's only two carbons, right? If you had CH3 carboxyl, this would be ethanoic acid. So you get rid of oic acid and you replace it with oil chloride, so ethanoyl chloride. Conversely, the common name would be acetic acid. So what did I tell you? You get rid of ic acid and you replace it with ill chloride. There you go, and that's how you do it. The rest of them all follow the exact same rationale. You have 3-bromo-propanoyl chloride or beta-bromopropionyl chloride. Same thing there. And the last one, you have 4-chlorobenzoyl chloride, 4-para-chlorobenzoyl chloride. Now, where does that come from? I just want to show you quickly. If you have, let me start over here. If you have this carboxylic acid, okay, and we looked at this evening, right? This is benzoic acid. Nothing new there, benzoic acid. Now, if I have a substituent on my benzoic acid, just going to shorten it like this. If I have it right next to it like this is called ortho substitution. If I have it one carbon away, okay, here's my carboxyl group. If I have the substituent like this, I call this meta. And if I have the substituent like this, then it's called para substitution. This only works for di-substituted benzenes. This is in my lecture videos, but I just want to be sure that you're with me on that, right? If it's ortho, they're separated by 1, 2. If it's meta, it goes 1, 2, 3 for the substituents. And if it's para, it goes 1, 2, 3, 4, like that. So that's where this P comes from, because instead of just writing out para, sometimes we just write the letter P. Instead of writing meta, we just write the letter M. And instead of writing ortho, we just put the letter O. So we could either call it 1, 2, 3, 4-chlorobenzoyl chloride, right? Benzoic acid, you get rid of oic acid, you change it to oil chloride, or it can be para-chlorobenzoyl chloride. There we go. So that's how you name an acid chloride, from either the common name of an acid or the IUPAC name of an acid. What about acid chlorides? Well, I can tell you firsthand that acid chlorides, like this one here, which you saw on the last slide, right? This would be ethanoyl chloride or acetyl chloride. Sometimes people call it acetyl chloride. That's fine with me. I don't care what you call it. Acetyl chloride. Why did I put a hydroxyl there when I'm talking about acid chlorides? Okay, I got carboxylic acids on the brain. Anyhow, acetyl chloride. I worked in a laboratory, and this is kind of a funny story. I worked in a laboratory when I was an undergraduate student, and I worked with a guy who was kind of crazy. And he would take acetyl chloride and he would actually pour it in the dishwater in the sink that we use to wash our dishes. And it makes a really loud noise. Like it makes it sound like a gunshot. It's that loud. And so that is because acid chlorides react very violently with water. Okay. Now, I'm never going to ask you about them being loud, but it makes a loud banging sound. Also, they have a very irritating smell. It says here noxious. Okay, um, it's like a sharp smell. Okay, it's not like a stinky smell like a sulfur compound. It's very sharp and very irritating. And since you have to keep them dry, you can't have them near water. You have to handle them very carefully. Okay. Now, what about their boiling points? Since we talk about boiling points so much in this class, they boil near the corresponding carbonyl. What's the corresponding carbonyl? Near an aldehyde or a ketone with the same number of carbons, okay? Somewhere in that neighborhood. Now it says here that they are good acyl group transfer reagents. What the heck is an acyl group? Let me show you. If you have a generic structure of an acid chloride, like this, we can put in all the lone pairs in our Lewis structure. This portion right here, it doesn't involve the chlorine. This is called the acyl group. Okay, that would be the acyl group. So when it says they're good acyl group transfer agents, all it means is that they're good at moving the acyl group around. Okay, they can put that acyl group on different molecules. We're going to look at an example of that in a little bit, but before we do, let's talk about the last important functional group that you have to learn in this chapter, and that's an acid anhydride, which has this generic formula here. Now, where would that come from? Let's think about it. If I took two carboxylic acids, okay, if I drew a carboxylic acid like this, and I heated it with another molecule of the same carboxylic acid, right? Imagine if you heated it really hard. Okay, I'll get rid of the exclamation points, it's not correct. But if you heated it really high, what could you remove? You could remove H2O, right? What would you be left over with? You'd be left over with this part, right? One of the oxygens and the rest of the other molecule, and you'd also be left over with a water molecule. And so that is actually one of the ways that you can form an anhydride. Okay, think about the name anhydride. What does it sound like? It sounds like losing water, right? Anhydride actually means without water. So if you have a symmetrical anhydride, that's one where both acyl groups are the same. Another way you could say it is that both of the R groups are identical. Symmetrical anhydrides are just named by taking the carboxylic acid from which they are produced and putting anhydride on the end. All right, let me show you these two here. If you have this acid, 2-carbon carboxylic acid, it is called ethanoic acid, right? So you get rid of the word acid and you replace it with anhydride. So you have ethanoic anhydride. Its common name is acetic acid. I get rid of acid, I replace it with anhydride, acetic anhydride. Benzoic acid produces benzoic anhydride. Now you might be wondering, if you're really astute, you might be wondering, hey, Mr. Dion, couldn't I have an unsymmetrical anhydride where maybe I have an acetyl group on one side and then I have a benzoic group on the other? Yeah, you can, but we don't really deal with those a whole lot in this class, especially in terms of nomenclature. Now, here's that reaction again, okay? And this is what I told you. Is the first thing I told you in this section, 14.4. I said, look, you guys, if you take 2 carboxylic acids, you mix them, and you heat it up really high, okay, you're going to end up driving off water, right? Because water has a boiling point of 100 degrees Celsius. We can get a reaction over 100 degrees Celsius, no problem, right? So we can make acid anhydrides that way. However, as it says here, they are typically not made that way, okay? Not generally speaking, we don't make acid anhydrides this way. So you might be asking, is there another way? Yeah, there is, and it's a better way. Let me show you. Okay, a better way, which just seems a little bit more complicated, especially to somebody who's just learning the subject of organic chemistry, is to take an acid chloride and a carboxylate and combine them together. Now I'm going to try to show you how this works. Okay, so this is a reaction you'll have to know. You're going to take an acid chloride, mix it with a carboxylate, it's going to give you an acid anhydride and a chloride. Here's the rationale. Now, this is beyond the scope of our class a little bit. But again, I like to try to explain things so that my students will understand it. Since you have a dipole going in this direction and this direction, okay, you have two dipoles, right? Oxygen and chlorine are both more electronegative than carbon. That means that these are going to be delta minus, right? They're going to be partially negative, and that renders the carbon partially positive. Look on the carboxylate, you've got a negative charge. What do we know about negatives and positives? Opposite charges, they attract. And so this is literally what happens. The negative charge on the oxygen is going to be attracted to the carbon of the acid chloride. And this curved blue arrow that I just drew represents the formation of this bond right here in the acid chloride. Well, what happens is when it hits the carbon right here, when it attacks that carbon or touches that carbon, it hits it so hard that it drives the chloride off. You end up with the chloride over there. So that's sort of a little bit of a description of what we call a mechanism of how the acid chloride is formed. Give me a thumbs up if you just kind of understand the rationale for how the acid chloride is formed. Opposite charges attract. They attract the attraction is so strong that it knocks the chloride out into the stratosphere, so to speak, and you end up with an acid anhydride. Good. Well, you might be wondering, how would I make an acid chloride? Well, there is a way to make an acid chloride. It's just shown here one time. It's when you take, the way you do it is you take a carboxylic acid and you treat it with SOCl2. This is called thionyl chloride. Okay, it's just a reaction we can use to make the acid chloride. Then you would treat it with the carboxylate, same old thing, right? The negative charge on the oxygen is going to be attracted to this carbon here. The chloride is going to leave, and you end up with the acid anhydride, and you end up with the chloride ion. All right. Well, what can you do with an acid anhydride? Okay. Once you've made one, are they good for anything? Yeah. Like I said, they're good. Sorry, I didn't say this, but they do have quite a few uses in organic chemistry. But one of them is shown here, and this is an acyl group transfer reaction. So remember, an acyl group is this portion here. Well, if you treat an alcohol with an acid anhydride, what's going to happen is, let me show you, the lone pairs of electrons on the alcohol oxygen, electrons are negative, they're going to be attracted to a partial positive charge of this carbon, and they're actually going to form a bond like this, and instead of using chloride, you're going to lose all of the carboxylate. Yeah. Now, you might be wondering, over here I don't have a carboxylate, Mr. Dion. That's because the carboxylate is going to combine with the proton from the alcohol to form a carboxylic acid salt. So a lot of students just choose to memorize these reactions, and there's nothing wrong with just memorizing them. But I think that having some kind of rationale for why they react the way they do can be really, really helpful. Okay, so again, just to review, we take an alcohol in the presence of our acid anhydride, and it transfers the acyl group onto this portion here to produce an ester, and then we also end up with a carboxylic acid. Here's another slide showing the exact same thing. I can show you that curved arrows again. Look, you have lone pairs on the oxygen. Remember, there's a dipole going this way, and there's also a dipole going this way. Therefore, the carbon is delta positive. The negatively charged electrons are attracted to this carbon right here. You're going to lose all of this over here, and you end up with your ester, and of course, you would also end up with your carboxylic acid left over as well. So you see again how the anhydride transferred the acyl portion, that's the acyl group, and then here's your acyl group now. Okay, so it just literally transferred it over onto the oxygen of the alcohol, and what do you have? You end up with an ester. I'm not really going to ask you anything in this chapter about phosphoesters, or really, because these come up quite a bit later on in the class. It says here that phosphoric acid, which is H3PO4, shown right here. So phosphoric acid reacts with an alcohol to produce a phosphate ester. So this is a different kind of ester. You should be able to recognize a phosphate ester. So let me throw that out there. If you see one in a police lineup, you should be able to pick it out. Okay, then that phosphoester can react with the second or third acid to give phosphoric acid anhydrides. And you've probably heard of adenosine diphosphate and adenosine triphosphate, ADP and ATP, from biochemistry. And these are examples of phosphate esters. Now here's the whole structure of ATP, which is what we call the cellular energy currency in the body. Anyhow, you can see that we have some phosphoanhydride bonds, and we also have a phosphoester bond in there too. But again, all I'll ask you really to be able to recognize is a phosphate ester. That will be good enough for me for the next quiz. A thioester. So if you take a regular ester, so here's my ester, like that. This is an ester. If you replace this oxygen at the top, okay, with the sulfur, like that, or sorry, that's a different kind of thioester. If you replace this oxygen over here with a sulfur, then you have a thioester. Okay, so a thioester. And acetyl coenzyme A is, we're going to see a lot of that molecule show up in the biochemistry section of this class, and it possesses a thioester in it. So you should be able to recognize a thioester as well. So these are all the reactions. There's a lot of reactions in this chapter. I would be crazy if I was to say, oh, there aren't that many. No, there's a lot that you have to know in this chapter. So make sure you're aware of those. And you have to know all these different reactions with carboxylic acids, esters, acid chlorides, acid anhydrides, and you should be able to recognize a phosphoester. Here are all of the examples of the reactions. You can find this in the summary of reactions at the end of the chapter in our textbook. It's a great resource. All kinds of good practice problems for you to try. And why don't we try a few practice problems before class is through here? We got time. So just give me a second here, and I'm going to go back to where we were the other night here. Just practicing with you, and I'm going to open up my book, and there's a couple of questions I wanted to look at. Second here on the floor in my office. So where were we? We did this one. We did up to 89. So I want to try question. Yeah, let's try some of these questions. So this is 14.70. Like those. Try. Yeah. Okay. Let's see here. Let's give one of these a try. So this is 14.73. Start with A. So if we have this guy plus I want you to draw the products of these reactions. All right. So I want you to try to fill these in. I'll give you a few seconds. I'll give you a few minutes. They're not easy problems. All right, let's take a look at these. So could anybody name the first reaction, 14.73A? Give me a name for it. It does have a name. Not a trick question. So this is where I take a carboxylic acid. We have a carboxylic acid plus an alcohol. And I put it in acid and I heat it up. So this is an esterification reaction. So what's going to happen? If we're taking that carboxylic acid and alcohol, we're treating it with an acid, and we're heating it up, we're going to end up losing H2O. That means we're going to end up with the following ester. 1, 2, 3, 4 carbons from the acid, and 1, 2 carbons here. So this would be ethyl butanoate, and of course I'm going to end up with water. All right, so there's an esterification reaction. The next one is where we're taking an ester. We have an ester, and we're putting it in water and acid. So here we're doing the opposite. This is the acid or acidic hydrolysis of an ester. We're breaking the ester apart. And remember that the carbon-oxygen single bond is weaker than the carbon-oxygen double bond. And so we're going to end up with a carboxylic acid and an alcohol. Our carboxylic acid will have 3 carbons in it, and our alcohol will have those 2 carbons in it. So we end up with propionic acid or propanoic acid plus ethanol. Could anybody give me a name for question 14.74D? It's got a really important name that everybody needs to know. No? Okay. This is a saponification reaction. So, saponification, which is the basic hydrolysis of an ester. So, same thing. The carbon-oxygen single bond is the weakest bond. But now, since we're in base, instead of producing a carboxylic acid, we're going to end up with a carboxylate ion plus our alcohol, which in this case only has 1 carbon. All right, and the last one, 14.76, shows we need 2 reagents to come together in acid and heat to produce an ester. Well, we saw up here that when we take a carboxylic acid and an alcohol and we heat them in acid, we end up with an ester, and that's an esterification reaction. So this is an esterification. And what's our carboxylic acid portion going to be? This part right here. And our alcohol is going to come from this portion right here. So let's write down our carboxylic acid, which is going to have a total of 4 carbons, 1, 2, 3, 4, butanoic acid or butyric acid. And our alcohol will only have 1 carbon, and so it's methanol or methyl alcohol for that esterification reaction. Why don't we try drawing a couple of compounds based on their names? So in 14.90, says just to write the bond line structure. So write bond line structure. And so we'll start with chloric anhydride and benzoyl chloride. Could also try 14.92, which is and over here we'll do all right, I'll give you a few seconds to think about these ones. Some nomenclature and drawing some structures. All right, let's take a look at the first one. We have valeric anhydride. So where's my black pen here? Valeric anhydride. There we go. So if we have a 5-carbon carboxylic acid, so 1, 2, 3, 4, 5, like this would be valeric acid. And so valeric anhydride is when we have our anhydride. Then we have 1, 2, 3, 4, 5 carbons here. 1, 2, 3, 4, 5 carbons there. Valeric anhydride. Benzoyl chloride is going to be a derivative of benzoic acid. Right here we have benzoic acid. And when we make an acid chloride, we drop the oic acid and we add oil chloride. So our benzoyl chloride is going to look like this. Just going to be benzoic acid, but the hydroxyl will be replaced by a chlorine like that. The next one is decanoyl chloride. If I had decanoic acid, it would look like this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, like that. So for decanoyl chloride, I'm just going to replace the hydroxyl with a chlorine like that. And for heptanoyl chloride, if I have heptanoic acid, it will have 7 carbons. 1, 2, 3, 4, 5, 6, 7. All I do is I replace the hydroxyl with the chlorine, and I get heptanoyl chloride, just like that.